Alright, Mr. Carter here. Let's begin filling out your chemical reactions worksheet. Start with your name, of course. Make sure it's all complete and not late because you're going to be turning in this assignment next class period. For you guys, that's Thursday. So you're going to want to make sure it's all complete so you get full credit for it. We're going to start with a little demonstration of how to balance a chemical equation. This is just like we did on Friday, but it's been a few days, so we're going to review it right now. Chemical equation is a great way of showing what happened in a chemical reaction. We started with some methane, also known as carbon tetrahydride, CH4, and we combined that with some oxygen in the air. We probably lit this on fire, and in doing so we created carbon dioxide gas and steam, water vapor basically, right? Clearly an exothermic reaction because we're burning this fuel to give off heat and so on and so forth. The things on the left side of the reaction, the things that go into it, are called our reactants, and the things that come out of it are called our products. Okay, so the first thing we need to do is make sure that the first law of thermodynamics, which says that matter and energy can neither be created nor destroyed, is holding true here. And it always does. We can't break it. So we need to make sure that our chemical equation isn't telling us that it's breaking it, right? So to do that, we count up everything that's found in the reactants and that's found in the products. So please write this along with me. For number one, we're going to list our reactants: carbon, hydrogen, and oxygen. Same thing with our products. We're going to list carbon, hydrogen, and oxygen. Now that we've got those written down, we're just going to count how many of them there are. So we're going to look for carbon in our reactants, and we see that there's just one. For hydrogen, there's 4. And for oxygen, there's 2. In our products, we have 1 carbon, 2 hydrogens, and 2 oxygens plus 1 oxygen for a total of 3 oxygens. The next thing we're going to do is just pick anything that's not balanced and balance it. Oh, and we can see right here that we ended up with fewer hydrogens than we started with, so we're apparently destroying hydrogen. That can't be. And we're ending up with more oxygens than we started with, so we're violating the first law of thermodynamics there, that we're creating matter, we're creating an extra oxygen. So we need to make this right. We need to basically correct this chemical equation. So let's start by balancing whatever is unbalanced. So carbons look good. Let's go down to the hydrogens. We have 4 hydrogens in our reactants and 2 hydrogens in our products. So therefore, if we put a little 2 in front of the H2O here, that 2, through the distributive property, is going to modify our hydrogens, but it's also going to modify our oxygens. But the reason we put a 2 there is, of course, 2 times 2 is going to give us 4 hydrogens, which balances our hydrogens. It is going to unbalance our oxygens a little bit because 2 times 1 is going to give us 2 oxygens, and we have 2 oxygens here from the CO2. So overall in our products, we now have 4 oxygens. That's too many oxygens, but the good news is if we want to add oxygens to our reactants, we can see that they come in groups of 2, which is nice. So 2 O2 molecules, 2 times 2 is going to give us 4 oxygens, balancing out the whole thing. So now it looks like we're good. So our final balanced chemical equation, I guess we could just skip that part. Our final balanced chemical equation is going to be CH4 plus 2 oxygen molecules creates 1 carbon dioxide molecule plus 2 water molecules. And presto, it's all balanced. Okay, now we're on the back side of the worksheet, the side that says how to balance more difficult chemical equations. So the front page was just basically review of what we've already done. Now we're going to try some slightly harder things. So if we have this chemical equation, calcium plus OH2, What that basically means is we have two OHs. So we have two oxygens and two hydrogens. Just like in math class, if the 2 is outside the parentheses, it gets distributed to both values, to the oxygen and also to the hydrogen. You wouldn't know how to say this yet, but this is called calcium hydroxide. So we have calcium hydroxide plus hydrogen phosphate makes calcium phosphate and water. So basically, the calcium and the hydrogen basically switch partners. Okay, just like with any equation that we've done before, we're going to follow the same general setup, and that means we're going to inventory our atoms. We're going to count up what we have in our reactants and in our products. So here we go. Make a little chart. For number 1, we're going to have our reactants over here, our products over here, and I've got calcium, oxygen, hydrogen, and phosphorus. And I want to put those guys in the same order over here in our products so I can compare them across easily. So I've got calcium, oxygen, hydrogen, and phosphorus. All right, my next step is to look at my unbalanced equation and count up how many of these guys I have. So I'm going to give you a couple minutes now to do this on your own before I show you the correct answer. So see if you can count them all up on your own right now. All right, let's see how you did. So if we look at the calciums in our reactants, we see that there's one here. It's not being modified by any subscript, so it's just one calcium. Oxygen, we see that there's one here that's being modified by that 2, so we have 2 oxygens. And over here we have 4 for a total of 6 oxygens. Our hydrogens, we have 2 here and 3 here for a total of 5 hydrogens. And our phosphorus, we just have 1 phosphorus here, so we'll just put a little 1 there. If we look over here at our products, we see that we have 3 calciums. In terms of oxygens, we have 4 times 2, 8 oxygens here, plus 1 here for a total of 9 oxygens. Our hydrogens, we have 2 hydrogens. And for phosphorus, we have 1 times 2, 2 phosphoruses. Okay, we're ready to begin balancing this. It's clear that it's unbalanced right now. So let's just pick one thing and balance it. Since it's at the top, I guess I'll start with my calcium. So looking at my equation, I'll put a 3 there, and then I'll count up what I've got. Here's a trick. I added a 3 here. That's going to modify this calcium oxide molecule. It's not going to modify this molecule over here, and it's certainly not going to have anything to do with my products. So what I can do right now, without having to count again, I could always count again. It would make me feel better, but just if I wanted to save time, I could just take the numbers from here, the last step in my products. Since I haven't changed anything in my products, I'll just take all those numbers and transcribe them down here. As far as my reactants are concerned, those are going to change, except for my phosphorus, which doesn't have anything affecting it here. So I guess I could say I still have 1 phosphorus. Since I have a 3 in front, I now have 3 calciums. In terms of oxygens, I have 3 times 1 times 2 for a total of 6 oxygens here, plus 4 there for a total of 10. And for hydrogens, I have 2 times 3 for a total of 6 here, plus 3 here for a total of 9. Okay, so looking at this now, I know that I'm still unbalanced. I guess I could balance my phosphoruses next, but here's a trick. If you take a look, and I've written this down below for number 3 for you, I have 9 hydrogens in my reactants. Because of the water in my products, I can only have hydrogens in groups of 2, right? If I have 1 water molecule, that's 2 hydrogens. If I have 2, that's 4. If I have 3, 6, etc. Since I can't have half a water molecule, you can't use fractions or decimals, I can only add them in groups of 2. That means I'm only going to have even numbers, 2, 4, 6, 8, 10, 12, etc. So the fact that I have 9 here isn't going to work for me. But I can take this 3, H3, and turn it into an even number relatively easy, right? If I had 2 hydrogen phosphate molecules, I would have 2 times 3 for a total of 6, which would make things nice and even. So let's do that next. So down below, we've changed this to 3 calcium hydroxide molecules. Don't mind that, just a little scribble. And here we're going to say we have 2 hydrogen phosphate molecules. Let's count everything up. And space is a little tight here, so maybe I'll use kind of a wider table this time around. CaOHP, AOHP. Okay, my calciums haven't changed since last time because I haven't changed this number. I had 3 last time, I have 3 this time, so I'm still going to have 3 calciums. My oxygens have changed. I have 3 times 2 times 1, 6 oxygens. And over here I have 2 times 4, 8 oxygens for a total of 14 oxygens. In terms of hydrogens, those have also changed. 3 times 2 times 1 gives me 6 here, and 2 times 3 gives me 6 there for a total of 12 hydrogens. And my phosphorus has changed as well, right? 2 times 1 gives me 2. Again, I haven't added any numbers over here to my product side, which is good for me. That means I can just use the numbers I had last time, 3, 9, 2, and 2. And looking at this, I can see that my calciums are both balanced, and my phosphoruses are both balanced. But I can see that I'm going to need more hydrogen over here on my products, and I'm going to need more oxygen over here on my products. But the good news is, there's a molecule in our equation that contains both hydrogen and oxygen. You know it, it's our friend water over here. So let's change the coefficient in front of, let's say, the H to give us 12 hydrogens. So what times 2 equals 12? Well, I think I know that. 6 times 2 equals 12. And let's put in the same coefficients we had from before, 2, 3. And then let's count this one up. Okay, so take a moment and count these up. Alright, well, if you, like me, notice that we didn't change anything over here in the reactants from last time, that means we can just use the same numbers from last time. So we've got 3, 14, 12, and 2. What we did change was our products, so these things are going to change. But we didn't change our number of calciums. We still have 3 there. We didn't change our number of phosphoruses, right? We still have 2. Our H's and O's will both be affected because we changed our number of water molecules. So let's take a look at that. 6 times 2 gives us 12 hydrogens here. If we have 2 times 4, that's 8 oxygens, plus 6 times 1, which is 6 oxygens for a total of 14. Well, look at that. Calciums are balanced, oxygens are balanced, hydrogens are balanced, and phosphorus is balanced. Hooray, all balanced. Alright, let's flip to the next page. So if we go to problem 5, we'll see that there was actually another way to solve that last problem. If you can see here, I did it with 6 calcium hydroxides, 4 hydrogen phosphates, 2 calcium phosphates, and 12 waters. And that works out for me. You can see my calciums, oxygens, hydrogens, and phosphoruses are all balanced. But there's a problem here. While this is balanced, it's not simplified. Meaning that just like giving a fraction in math class, you should have your chemical equation in simplified form. And it looks to me like all of these coefficients, 6, 4, 2, and 12, can all be simplified, right? Because what number goes into 6, 4, 2, and 12? Well, they're all divisible by 2, right? So if we were taking that in mind, we would rewrite this equation with all the coefficients divided by 2 down below. See if you can do that now. Alright, good. So if we divide all these guys by 2, we get 6 divided by 2, which is 3 calcium hydroxides plus 4 hydrogen phosphates makes 2, oh wait, I didn't simplify, 2 hydrogen phosphates makes 1 calcium phosphate, and of course if there's just one of it, right, divided by 2, divided by 2, divided by 2, divided by 2. If there's just one of these guys, you don't need to write any number at all. We can just write calcium phosphate and 6 waters. And if we counted everything up, we're going to see we got 3 calciums on both sides. We've got, what do we have, 14 oxygens on both sides. Looks like 12 hydrogens on both sides. And 2 phosphoruses on both sides. And this thing is totally balanced. So, hooray, we did it. And you'll notice, if we flip back to that last page, this is the same one we got for our correct answer earlier. 3, 2, 1, and 6. 3, 2, 1. Oh, sorry. 3, 2, 1, and 6. So whatever answer you get, always check it to make sure it's simplified. If there's a 5 or a 3 or a 13 in there, for example, you know that it's simplified, right? Because those are all prime numbers. They can't be divided by anything. If it's like this, and everything can clearly be divided by another number, such as 2, then you got to do that. Simplify it, divide them all by 2, and you'll get, hopefully, a correct answer, like we did here. All right, you guys are ready to attack some of these problems, but let's first check out problem number 3. So, if we look at problem number 3, we see that we've got aluminum. Okay, that's easy to work with. We've got iron. That's easy to work with too, right? Because with just pure aluminum, we can put whatever number we needed here. If we needed 27 aluminums, we could just put a 27 in front. If we needed 312 irons, we could just put 312. So we really are going to worry about these two. And again, not the aluminum and iron as much because we can put in whatever we need, but we're going to worry about the oxygens. So we have 4 oxygens here, and we have 3 oxygens there. Okay, so if I were to go in groups of 4, my options are 4, 8, 12 oxygens, 16 oxygens, 20 oxygens, etc. If I were to go in groups of 3 over here, I could have 3 oxygens, 6 oxygens, 9 oxygens, 12 oxygens, 15 oxygens, whatever. So I guess the easiest way to solve this would be to find the lowest common denominator of 4 and 3. So what number contains both 4 and 3 and is the smallest of these possible numbers? Well, we could get that by just multiplying them together. And of course we get 12. There's no smaller number that contains multiples of 4 and 3. So in order to get 12 oxygens, we would need to have a 3 here and a 4 here, right? 3 times 4 is 12, 4 times 3 is 12. Let's count them up. Here are reactants, here are products, Al, Fe, and O. Al, Fe, and O. We have 1 aluminum, 9 irons, 3 times 3, 3 times 4, 12 oxygens. Here we have 4 times 2 aluminums for 8 aluminums, 4 times 3, 12 oxygens, and 1 iron. And like I said, the reason we didn't worry about the aluminum and the iron first is because they're going to be super easy to balance because they're all by themselves, whereas the oxygens are kind of tied up in this bigger molecule, right? Iron oxide and aluminum oxide, they're both ionic. So now that they're balanced, we can just take a look at our other guys. Well, we have 1 aluminum here, we have 8 aluminums here, so we're going to want a total of 8 aluminums over on this side. So what times 1 equals 8? Well, 8 times 1 equals 8. So that's going to balance our aluminums. Last thing is balance our irons. We have 9 over here. 1 times 9 equals 9. So if we put a 9 there, we're good to go. So aluminums are balanced, irons are balanced, and oxygens are balanced. Last step would be to check this and make sure we can't simplify it. Is there any number that goes into 8, 3, 4, and 9? Well, 3 goes into both 3 and 9, and 4 goes into both 8 and 4, but no one number goes into all 4 of these, so that means we can't simplify. We have to be happy with it just the way it is. So that means perfectly balanced. That's our final answer. All right, make the most of your practice time today. Remember, your packets are going to be due at the beginning of next period. That's Thursday. I'll see you then if I'm better.